Cool. So, one, two, three, boom, and welcome to another episode of the Trenches series, where boom is quite fitting today because we're going to be talking about rockets. Hi, Luka. How's it going?
Good. Yeah, pretty good.
I'm actually super excited about this episode because I know literally nothing about rockets. I'm going to ask you a couple of very naive questions, I suppose. And I know a bit about you already because we talked beforehand. Just to give the folks outside listening a quick idea, what kind of rocket project are you working on again? Where? What do you do?
Yeah, so I'm Luka. I'm a junior at MIT, Massachusetts Institute of Technology, in Boston, in the United States. I'm a part of MIT Rocket Team, and what we work on is a bunch of rocketry projects. We usually do one at a time, and then when we're done with one, we try to learn from that one and continue. Our main goal is trying to reach space, so the internationally recognized Kármán Line at 100 kilometers above ground. And yeah, we're trying to get there as soon as we can, but we still have plenty of rockets to go. Right now, we're building a two-stage rocket that is going to go to around 60,000 feet or 20 kilometers. And after that, we have maybe one or two more projects before we try to actually before we attempt the space shot.
How many rockets did you have so far?
That's a good question, and I don't know if I know the exact number. Let's see. So we started with competitions somewhere around 2013 to 15, way before I joined, way before I came to MIT. And after that, we've had something called Project Hermes. So after we decided we're going to go beyond the competitions because those usually cap at either 10,000, 30,000 feet. So we said we're going to go build bigger rockets than that. We did Project Hermes 1, which was pretty successful. Then I joined my freshman year. We did Hermes 2, which was supposed to go up to 80,000, and it didn't succeed. Then half a year later, we did Hermes 3, just before the pandemic started. And also we did two-stage rockets as kind of a test projects for our staging technology alongside the Hermes rocket. So in the summer of Hermes 1, which was 2019, we also did staging demonstrator 1. And then in January 2020, as well as Hermes 3, we did staging demonstrator 2, which was actually very successful, except that the parachute didn't deploy. We had all of our other systems working, so we ended up finding the rocket buried under the sand. It was like a 4 feet tall rocket, and it was buried 6 feet under the sand. It was crazy. When I stood in the hole, like you couldn't see me out of it when we dug it out. And yeah, so
I was actually just wondering when you said so earlier attempts didn't succeed. I mean, what basically happened or what can happen with? I mean, I guess everything can literally happen with these attempts.
Yeah, so it's really a complicated process, and a lot of things can go wrong. So when people say it's not rocket science, we're actually doing rocket science. So things are pretty hard. We really try to be very rigorous about testing, making sure we anticipate all kind of possible failures, all kind of events that all of our parts can withstand any stresses and everything. We have this on one side, and then on the other side, our stuff needs to be performant enough to reach certain altitudes and speeds. So it's really, and then also launch procedures. You can't, and nothing can go wrong during integration the day before, the day of. You need to check all systems for malfunction or any errors, everything. So generally, things that go wrong are, we're not perfect at being able to calculate what's going to happen to a rocket. So we've had some issues with fins. We're also not that great at making fins out of carbon fiber yet, just because we don't have the expertise. So we're building up to that, doing a lot of testing as much as we can. So fins have been our problem. And then for that one that didn't deploy the parachute, we actually don't know exactly what happened. So we need to We suspect that it was an issue in the wiring because that was considered a side project, so the wiring wasn't done as well
Right.
as the other one. But we don't know exactly. So
And I guess it's
just
not too easy to find out. I mean, after the
yeah.
fact.
No, yeah. After, I mean, the rocket was squished. Like the parts that weren't metal were literally compressed to a tenth of their size. It's really hard to find out what exactly happened once you have everything compressed in the ground. Yeah.
Right. Just to get back to the basics with the naive questions, you mentioned it's now a two-stage rocket. And I suppose the stages have to do with how high the rocket can go, or what do the stages essentially say?
Yes. So so one of the most basic principles that we operate on is called the rocket equation, which basically just says you can go as high as much as the proportion of the mass that you're willing to lose. So when you start losing mass because you're burning propellant, you get more and more kind of extra ballast from the structure that was holding that propellant. If you drop some of your structure, which is the lower stage, you get a huge benefit because now you're carrying up a smaller mass. So that's the biggest advantage of using multiple stages, and the reason that all bigger rockets that companies use and national programs have multiple stages, simply because it's easier to transport a smaller mass up, and you don't want to be holding your old empty reservoirs. But there are certain challenges with it. So so far there's one team that has reached space, and they've done it with a single stage. So we would be the first collegiate team to get up to space with a two-stage rocket.
All right. How is that? How is that, by the way, organized? So, I mean, you're all students, I suppose, or most of you are students working on the project. I suppose a couple of professors also, or how is that basically organized?
Yeah, no, it's completely student run. We have a few grad students, but they don't really lead the project. They are usually there for advice and support because they have a lot more expertise than undergrads, because we just come in and learn this from scratch. But there are no professors leading this or anything. We have the department supports us both financially and somewhat technically, but their support technically is mostly just participating in reviews. And they once we're done with the project, we have something called a critical design review, where we present it to them at our design, and they just say they give us feedback or anything, and then we have a flight readiness review where we present what we're going to do, and they give us the green light. But that's mostly it. They don't really participate in the design. There's not that much feedback that we get from them except on those two events, and that's it. So other than that, mostly undergrad run. Yeah, people in their like second and third year will usually be in like executive positions.
Right, because I was just asking. I mean, I suppose it's a multi-year project, and then it might also have a fair amount of rotation among people. Because I mean, you finish your studies, or you go on, and you drop in, drop out. I don't know, but or is the team basically how many people do you have, and how many people fluctuate, or how stable is the team?
Yeah, that's a great question. We do have some issues sometimes with some people leaving and knowledge transfer, so we need to be very careful about that. So we really keep it in our minds when we plan on what we're doing, that we say, look, we need to build this, but we also need to make sure to teach new members and transfer knowledge, because one of our biggest objectives is to teach members the necessary skills to work in the aerospace industry. It's one
Right.
of our official goals as a team as well. That's quite tough, because it's not like a company where some people just stay forever, and like nobody's here forever. Everyone leaves at some point to go do something else, and people, even while they're still at MIT, get other projects. Usually, just get involved with research, have to do grad school applications. Just kind of grow out of the team, and we even lose those people. But right now, I think we're at around 70 to 100 members. It's really depends on how you count. If you count like in the broadest sense possible, you could get up to 150. But that's the people that showed up once, or just like were involved, are on a mailing list or something. For the active members, I think I would say around 70. And then of those 70, well, right now we don't get to do a lot of things in person, so it's hard to count. But the last time we did, at launch, we had like 45 people there, and there were at least 15 more people that did a lot. But then, as you go in, the number, as you raise the bar for involvement, the number of people decreases. So, there's only maybe 20, 25 people that really put a lot of work into this.
Most important question. So when you launch a rocket, what does your headquarter look like? Do I have to imagine like a NASA headquarter kind of, or do you all sit in the cafeteria and watch, or what's that look like?
No, yeah, it can get quite hectic, but we do have a very low head count. We don't have anyone who doesn't also work on the rocket there really. So we really need to use every single person for something. So everyone will have their assignments, and also we're not really overflowing with money. Like we spend all of our money on building the rocket and then travel expenses and everything. So once we get to we usually get like an Airbnb near the launch site in California for a couple of days, finish the build process, so some people have to be in charge of food because there's 40 people that need to be fed because they're all working on the rocket all day.
Does that
some
mean
people
pizza nonstop, or what kind of food?
No. We had someone in charge of cooking, and a couple people, like a lot of people helped, and they just cooked for everyone, and it's quite a big undertaking. But yeah. And then in terms of the launch, we are split into teams. So this launch in January was actually the first one that we actually had a separate away team that had its own all plans for the day and everything. So what happened was we launched at FAR, Friends of Amateur Rocketry. They're really great people and give us a lot of support and everything. It's a great amateur rocketry launch site, and it's in the Mojave Desert, just 3-4 hours out of LA. And it's surrounded by some small mountains. And I remember when I went to my first launch in the morning, we woke up at 5 a.m. and I saw the sunrise. It was really beautiful. And I saw those mountains and I said, hey, we could just put some people on those mountains. It'd be really cool to see the rocket. And also in terms of radio connection, we'd get a better angle for aligning our antennas with the rocket. Right. So next time in January, we actually did send a couple people there, including myself. And well, the views were great, but it also worked amazing because we actually maintained a link to the rocket until it crashed, and the people at the launch site didn't. So we had 8 people at the away team and 34 at the launch site. There were people had to assemble the rocket, do everything, place a bunch of cameras, be in charge of electronics, everything. There's so many roles and so many things that and assignments that people have during launch. And then the away team, we just had a bunch of antennas. I mean, so did they at the launch site, and some cameras as well to try to capture things. And we even had a drone that was some really good footage. And yeah. So
if you have that footage, please share it. I mean, I'd love to link it. Or I'm quite sure my team was actually super excited about this interview. They all wanted to know what we're going to talk about. If there's pictures, if there's movies or anything. So please share anything you have, with us, and we're going to link it.
All right, sounds good.
To get a bit more into the rocket itself, I know there's an embedded controller, multiple ones involved. What exactly, for novices, what does the embedded controller of a rocket do? What's it responsible for?
Yep. So that's a good question. It really depends on how far along we are in our process, because this team started with commercial off-the-shelf altimeters, but basically all of the electronics in the rocket is called avionics, stands for aviation electronics, and basically we'll do a couple things. One very important thing is it needs to fire the parachutes. So it needs to be configurable to say, we want to fire the parachute at apogee, which is the highest point of the flight, because that kind of makes sense. Before we start falling down, we want to fire a parachute so we never start falling down too fast. And then usually for higher altitude flights, if you fire a large parachute on top, you're going to float very far away because the winds are pretty strong. So you want a small one to really descend quickly, and will fire a larger parachute so that you touch the ground softly, maybe around like 700 meters above ground, something like that. So parachute deployment is one. Then a radio connection. Again, not all computers have this, but we actually have had our computer have a successful radio link, as I mentioned, for the first time in January 2020. We actually maintained a radio connection through the whole duration of the flight, which was pretty impressive, given all the speeds and alignments, everything. And the distances, we got up to 10 kilometers, which means the whole distance was, that times at least root of 2. So that was really a good moment for us. And then we have estimation. So I mentioned, you want to fire the parachute at apogee. How do you know that you're at apogee? You have a bunch of sensors like accelerometer, GPS, barometer, and you need to kind of put all of those together to get an estimate of your altitude and just location in general and speed and everything. You want data from the flight, so you need some kind of aggregation so that you can say, okay, we got to this altitude, this velocity, and so on. And then data logging. All of that data that you compute and send down over radio, you also want to log. Right. So that you can actually, because radio doesn't have the bandwidth to send down all the data, although we're trying to get our bandwidth as high as possible, but still, we want to have some kind of logging, so we have some persistent storage, and then once the board, if it doesn't crash, hopefully the flash chip is preserved and we can read the data off of it. Right. And then there's more, but I'll be short. There's cameras. We want to control, turn them on and off, because the rocket sits on the pad for like 20 minutes, half an hour, maybe hours on end, depending on how the launch procedures go. But the flight's 7 minutes long, so we don't want to be running the cameras. We don't want to be running the battery for too long. There's a lot of stuff that needs to be controlled and turned on and off as we go.
How many people out of your team work on these embedded controller stuff, and what programming languages are being used, and how is all of this simulated, and how is all of this tested? So there's a ton of questions actually involved, but let's start from the beginning. So how many people, again, would you say work on this sort of software, basically?
Yeah, so our sub-team is called Avionics, and we're actually the largest sub-team. I think both because there's a lot of work, we have software and electronics, everything in one sub-team, and that's kind of the biggest part of the rocket, because every other part of the rocket, even though it's physically bigger, the rocket's split into multiple components like propulsion, structures, composites, and recovery. And those things are all, smaller in total. We're all of them combined, they're bigger than us, but we're the biggest sub-team. Both because of that, and because at MIT half of the people are computer science or electrical engineering, so we do get a few more people, which is great because we need them. We really need that. So I would say around 20 to 25, maybe 30. That's on the high end, but very active, somewhere between 10 and 15.
And programming language wise, how is this stuff programmed?
Yeah, we try to keep it simple and, not involve too many programming languages. So we do our embedded stuff in C++, and we use Python for any scripts. And we have a ground station, which is basically a desktop program you run on the ground, on the computer, that lets you communicate with the rocket, with, of course, the support of some radio hardware. But
okay, I see. So that means in the end, you're going to have one source repository, I suppose, where your C++ and the Python code lives in, or how is that structured?
Yeah, so we actually have a couple. We have one for all of our flight software, and we started a new repository now because we're starting a new computer. We have a bunch of old repositories for old code, and then sometimes we make repositories for some tools or libraries. We're still thinking about, open sourcing some of the code, because really there's no reason not to. So we're going to see how that goes. But yeah, there's some libraries that we have that we need to modify, so we make our local copy of it. For example, we have this build system that we use with CMake and Embed. That's kind of niche, so we use a library for that. Actually, I've helped write that library with one of my friends from USC, RPL, which is the other team that actually made it to space. They're based in University of South California in LA. So that's that, and then we have obviously one repository for our Python code in for the ground station.
Right, and then what does a build pipeline actually look like in your universe? So you have your C++ code. In the end, it has to end up on the rocket, I suppose. But what does a build pipeline really look like?
Yeah, so as I think a lot of embedded teams do, we don't really, or at least we used to not have like a very proper pipeline. What we'd do is just, we'd have our code, we just compile it locally and upload it to our computer. Very recently, we've added some kind of continuous integration where we try to build and test it. So we started using unit tests when I joined the team. That was actually one of my first projects. And I remember because, I had to rewrite most of the code because it wasn't in a structure that was unit testable. So that made me really familiar with everything. So that was really a good start. But yeah, since then we've been doing unit testing, and that's been very helpful in, getting our test code to actually work. So now we have this kind of...
Do you have an example of a unit test, an avionics unit test, for example, just what that would look like?
Yeah, sure. For example, our radio stuff is split into a bunch of modules. One module is called a radio abstraction layer, which kind of talks to the drivers for the chips and receives input from, let's say, telemetry, another module. So when we test telemetry, we say, okay, we expect that this is going to send out this specific packet every and then, every 3 times a second or something like that. So
right.
Then we run it, and then we say we expect that radio abstraction layer receives this kind of packet this many times, and so on. And then we try different configurations and say, when we configure it like this, we expect to see that, and so on and so forth. So that's an example. And then, we try to unit test as much as we can. But when it comes to embedded, there's a lot of stuff that you don't want to sacrifice in performance. So it gets really tricky to actually do proper unit testing. So we also do other kinds of testing.
What other testing do you do?
So a lot of this is, we're kind of starting and adding new stuff. But one of the testing is going to be like a simulator where we're going to compile all of our code to run on like a normal operating system instance, not on the embedded hardware yet. And then we're going to simulate all the hardware and try to see if the whole code base can work together. So that's kind of the next step from unit testing, because we still don't have hardware, but we run everything together so we can see the interaction of different components. Then the next step would be to upload the code to hardware and then test it on the hardware. And then the last step is something we haven't actually done that much because our code would have to be finished for that to happen. And we would have to be not on a deadline that's approaching quickly. So we're really hoping to do that in the fall, which is flight testing. So we want to put our flight computer onto a different flight where it's not actually in charge of deploying parachutes. It just logs the data and pretends like it's in charge. And then we will look at that data and see, okay, this works correctly. And then we'll see, look, actually here it made a mistake. Let's fix that. So that's the last stage of testing before we put it on our flight. And if our flight computer is not ready until this next flight, which is probably going to be in January 2022, we're going to put it on there along with some other commercial off-the-shelf altimeters. So those are going to fire the parachutes, and ours is going to have the final test. And then if that works, we can actually say, look, our computer works. Let's get rid of the commercial off-the-shelf ones and use ours to deploy the parachutes.
Right. Because you just mentioned deadlines. I was wondering if I got to ask, how is the project actually structured in terms of deadlines? I mean, who says when the next goal is going to be? How do you decide on all of that? Is there like a I don't know, you have a set of 5 people controlling the project, the overall, like, say, flow of the project? Who makes deadlines? Who decides what's next and all of this stuff?
Yeah, it's really integrated. I mean, a lot of startups will brag that they have a very flat structure. We have a really, really flat structure. We have an executive team. So there's president, vice president, treasurer, social chairs, launch chairs, recruitment chairs. Sometimes some of those roles are condensed into one because one person wants to do multiple, because some of them are just not as much work. Obviously not president and vice president. So that's one layer of like executive exec. Then also on executive, kind of on team leads, we say, are sub-team leads. So each sub-team has one person as in charge, and all of those people together can kind of form the like executive part of the team. And these people meet weekly. I used to be in that. I'm not anymore. Meet weekly to decide on all those goals. And, obviously, like president and vice president would try to plan this a little more. But generally, there's kind of like a shared idea on when things should happen. And a lot of times, things will change based on the inputs from different teams. Because let's say propulsion says we need more time to characterize this propellant, then obviously the whole team is going to push the goals back. So we really try to be very, interactive about this process based on how sub teams are doing. Because if one sub team isn't going to make it, they just aren't going to make it. None of us are doing this full time. Everyone's on pretty much a full class load at the same time as doing this. In the summer, people have internships or jobs, and this is really a side thing. So it's really like incredible to see, everything so much done on top of all the other things we do.
I was about to say that it is super incredible to see and to hear that you actually make something fly, being a part-time project with undergraduate students actually. So sort of a last question on launch day. How nervous are you, or is everyone basically? I mean, so is that like everyone is like, is it like a constant, some sort of an anxiousness, like before like a boxing fight, I suppose, where you think, oh, what is going to happen? What is going to happen? And then I mean, what's that look like?
Yeah, I mean, that's a pretty good analogy, I would say. I think generally a sports game is a good comparison of how things feel, except it's like a very important game. It's like I don't know, probably feels like a final of a competition that, you don't always reach and doesn't even happen every year. It's really tense. But most of the time, honestly, you don't have time for that. You are kind of in a trance of just going through all the procedures, making sure everything happens, I remember like on the away team, there was a couple of times when the launch site fell a little behind on something. So we had time to just sit and relax. And that was the time when our nervousness kicked in a little more. I mean, it's a lot of fun. As I said, the desert is beautiful by itself. There's a lot of people. It's really a great time. There's a lot of nervousness, but also it's really just so busy. You have to care about so many things that really occupies your mind for most of the day. So, you're nervous when you get there, but once you get out of the car and start doing things, you kind of forget about that and just need to focus on your part of contributing to this to make sure nothing goes wrong.
Right. Well, I'll tell you what, that has been super interesting, and I have the feeling I could go on for hours essentially. I mean, that was just a half an hour, but we just scratched the surface, I suppose. But in any case, Luka, thank you. I really appreciate your time and you explaining us what you folks are up to. And I wish you the best of luck with the rocket and your future plans. Actually, thank you for the interview.
Yeah, thank you so much.